Lesson 9 is all about finding real zeros of polynomials. We begin by finding potential or possible rational zeros. Until now, we've been given a starting zero to help us find the zeros of a polynomial. Now we'll actually learn how to discover that starting zero on our own. This lesson comes from section 2.4 in the college algebra textbook, and we begin with the rational zeros theorem. Suppose we have a polynomial with the usual leading term of a sub n x to the n and the constant term of a naught. Well, this polynomial is of degree n, and note one thing here, the constant term here must be an integer, so a naught must be an integer for this theorem to work. Then if we do have a rational zero, we'll call that rational zero r, then r is of the form p over q, where the integer p is a factor of a naught, and the integer q is a factor of the leading coefficient a sub n. Let's look at an actual polynomial here. F of x equals 6x cubed minus 3x squared plus 2x minus 4. So if I want to find the potential rational zeros of this polynomial function, I'm going to start by figuring out, well, what is a sub n? The leading coefficient would be 6. The constant term here is negative 4. So let's start by seeing if we can figure out what p would be. So p is going to be a factor of the constant term, negative 4. So if we take negative 1 times positive 4, we get negative 4. If we take 1 times negative 4, we get negative 4. If I take 2 times negative 2, I get negative 4. So let's look at the possible values for p here. Plus or minus 1, plus or minus 2, plus or minus 4. What about q? Well, 6 is the leading coefficient here. What numbers would I multiply together to get 6? I could take 1 times 6, negative 1 times negative 6, 2 times 3, or negative 2 times negative 3 to give me 6. So those are all the values for q. Now we want to figure out what would p over q be here. So p over q would be, I could think of this as plus or minus 1, plus or minus 2, plus or minus 4 divided by plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. When we break that down into all the possibilities, we're going to end up with plus or minus the integers of 1 or 2 or 4 over 1 or 2 or 3 or 6. So let's see what we get here. We would first of all, this is the order I go in, so you need to figure out what order you want to go in. I would usually start with the 1 here, or the first number that appears in the numerator, and I would take 1 over 1, 1 over 2, 1 over 3, 1 over 6, then I move on to 2, 2 over 1, 2 over 2, 2 over 3, 2 over 6, and then moving on to 4, 4 over 1, 4 over 2, 4 over 3, 4 over 6. Okay, now we'll simplify. Let's see what we get if we simplify here. So 1 over 1 is 1. We have 1/2. We have 1/3. We have 1/6. 2 over 1 is 2. 2 over 2 is 1, which we already have. 2 over 3, 2/3. 2 over 6 is 1/3, which we already have. 4 over 1 is 4. 4/2 is 2, which we already have. 4/3, and then 4/6 is 2/3, which we already have. So here are all the p's over q's in simplified form. The only other thing I might do is maybe write these in order. You actually have a fine answer right here if you want to leave it this way, but if you want to write your numbers in order, you would have the potential rational zeros here of plus or minus 1/6, plus or minus 1/3, plus or minus 1/2, plus or minus 2/3, plus or minus 1, plus or minus 4/3, plus or minus 2, plus or minus 4. And you'll get some practice with this in the exercises. One thing to note here, these are potential rational zeros. The actual rational zeros, and I'm not going to even display them here, they're kind of ugly, but the actual zeros, you would have 2 imaginary zeros, and you would have 1 irrational zero. So that won't be the case with the problems that you work through for this section of the textbook, but this is possible. These are only potential. They don't really guarantee you anything. Okay, let's go on to the first try on your own. Use the rational zeros theorem to make a list of possible rational zeros of the polynomial f of x equals 3x cubed plus 7x squared minus 2x plus 4. And we're going to take a look at Descartes' rule of signs. Suppose f of x is a polynomial function written in descending powers of x. So we have f of x, polynomial function, written in descending powers of x. Descartes' rule of signs is going to tell us how many positive real zeros and how many negative real zeros we have. It's not actually required in this course, at least at the time that I'm making this video, but it may help you out sometimes, so I did want to include it. Okay, so how it works, if P denotes the number of variations in sign of the formula for f of x, then the number of positive real zeros, counting multiplicities, which we'll talk a little bit more about later, is one of the numbers p minus 2, p minus 4, and we keep like going p minus 6, p minus 8, whatever, until we get to either 0 or 1. Then if n denotes the number of variations in sign in the formula for f of negative x. So up here we had f of x. For negative zeros, we look at f of negative x. Then the number of negative real zeros, counting multiplicities, is one of the numbers n minus 2, n minus 4, and we keep heading on down until we get to either 0 or 1. So this is easiest to figure out what's going on from an example. Let's do one. Say we have f of x equals 3x cubed minus 6x squared plus 2x minus 4. And then to find the number of positive real zeros, we look at the number of sign changes. So if you think of this as being plus 3x cubed minus 6x squared plus 2x minus 4. How many times do we change sign as we go from left to right? So right here, plus to minus, we go 1 sign change, 2 sign changes, 3 sign changes. So the number of positive real zeros, counting multiplicities here, would be 3, or we drop down by an even integer. So you can think of that even integer if you just use 2. 3 minus 2 is 1. And we stop at either 1 or 0. So the number of positive real zeros here, counting multiplicities, is either 3 or 1. What about the number of negative real zeros, counting multiplicities? Well, in order to figure that out, I need to find f of negative x, which would be, we look up at f of x, and wherever I have an x, I put in negative x in parentheses, and then I simplify. So I would end up with f of negative x equals negative 3x cubed minus 6x squared minus 2x minus 4. And again, we look for the number of sign changes. So here we have negative, 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 negative. No sign changes. That tells me that there are 0 negative real zeros. And this is where Descartes' rule of signs is most helpful. If you know that you don't have any negative real zeros, we don't need to test any of those potential rational zeros that are negative that we found. So this will save some time. Let's look at another example where this time we use Descartes' rule of signs to determine the number of positive and negative real zeros of g of x equals 2x to the 5th minus x to the 4th plus 3x cubed minus 5x squared plus x plus 7. Okay, let's start by looking for the number of positive real zeros. We have plus, minus, plus, minus, plus, plus. So we change zeros. 1, 2, 3. We change signs. We change signs 1, 2, 3, 4 times here. So the number of positive real zeros, counting multiplicities, would be 4 or 4 minus 2 is 2, or 2 minus 2 is 0. Okay, so now for the number of negative real zeros here, counting multiplicities, we find g of negative x. G of negative x, we just replace x with negative x in parentheses, and then we simplify to get g of negative x is equal to negative 2x to the fifth minus x to the fourth minus 3x cubed minus 5x squared minus x plus 7. And so it looks like we have one sign change here. And so the number of negative real zeros would be 1. Okay, so that's it for today. Let me know if you have any questions about anything here.